Since we aren't covering a few sections in chapter 4, when you look at, if you do look at rather, the exam 3 review, just note the sections we skipped so you don't do those problems. Remember when you're taking these things from my math lab, the section number is up here at the top in the top left. So this is 4.2. So we didn't do anything from 4.2, so you can skip those.
What do those last two numbers mean again?
The textbook example,
okay.
like if you look in the textbook. So just keep that in mind. I don't know how many of y'all actually go through that. You have quite a few homework problems as it is, but anyhow. In 4.9 we left off with the constant multiple and the sum rule, which, you know, allows us to put together in a more efficient way, really, polynomials. So we did look at that example. If you just want to go from this step to this step, that's fine. It's to be expected after you've done a few of these. You don't have to write all of this stuff out that we wrote to show your work. So did anyone have any questions on that? One thing to be cautious of is at this point we don't have a way to find the antiderivative of a product or a quotient. So we get one other technique of antiderivatives in chapter 5. So if you're presented with a quotient or a product, you cannot take the antiderivative by quote unquote distributing the antiderivative through a product or through a quotient. So let me just write this here. If we have the antiderivative of f times g with respect to x, it's not the antiderivative of f times the antiderivative of g. Why would that be, just based on our knowledge of derivatives?
Because with the rule, it's there's that sum in there. It's the left times the derivative of the right.
Yeah.
Plus the derivative of the left times the right.
Right.
So naturally, you think anyway, you'd be able to solve it just by, doing a right to left or. Yeah,
exactly. With the derivatives, you have a product rule, right? So if we're trying to figure out what function's derivative gives us a product, f times g, just think about like having to reverse the product rule. The product rule has a sum in there. So this is not true, nor is the antiderivative of f over g the same thing as the antiderivative of f divided by the antiderivative of g. So those functions are, if g is not 0 here or 1, it could be a special case, but in general, you don't anti-differentiate across a product or a quotient. And even when you learn how to do stuff like that, it's much easier to try to simplify before you take an antiderivative. So like example 2, you wouldn't want to take the antiderivative of the top divided by the antiderivative of the bottom. It wouldn't work. But we could simplify this expression first before we take the antiderivative. So it's not every single problem that fits this bill, but if you notice the function can be simplified, then simplify it first before you take an antiderivative. Just like with derivatives, if you simplify before you take a derivative, you're going to have an easier thing to deal with. So we need to simplify this quotient first. And rewrite this as each term in the numerator divided by x squared. So we have x to the 5th divided by x squared. minus 2x cubed divided by x squared, and we have x squared divided by x squared. So that's what our function simplifies to, and that's what we'll take the antiderivative of, because we have a rule for all of those terms separated with addition, subtraction, multiplication by a constant, right? So what is the antiderivative of x cubed? X to the fourth over 4, right? We add 1 to the power that's present, and then we divide by the same result. What's the antiderivative of minus 2x?
Minus x squared.
Minus x squared. Does everybody agree with that? Take the derivative of negative x squared to get negative 2x. And the antiderivative of 1.
X.
So that's like 1 plus x to the 0. Okay. And then the antiderivative involves some arbitrary constant. So just try to remember that. Okay. Does anyone have any questions at this point? So other than the ones on the formula sheet that was provided, the only thing we can find outside of those is or the technique that we have rather is the power rule. So if you see products, quotients, stuff like that, don't try to integrate or find the antiderivative of those. So the antiderivative of 4 root x minus 4 over root x. So
Simplify that.
So if you wanted to try to simplify that, what would you do?
4x minus 4 over square root of x.
4x minus 4. So how would that be obtained? Like, what would you do?
Just multiplying the 4 square root of x by square root of x on top and bottom.
Okay, so if we tried to take 4 root x minus 4 over root x, if we tried to simplify this first and just multiply through by 1. So just, be aware that if this is the function that we're taking the antiderivative of, it's assumed that x can't be 0, because what's present in the original function is the root x in the bottom. So if x isn't 0, it's fine to multiply by root x over root x. And so what would that give us?
For the numerator?
Yeah.
X minus 4?
So yeah, the root x would cancel with this root x, but it would be 4 over this root x, right?
Yeah, 4 over root x. 4 root x.
Minus
4 root x.
4
4 times root x.
4 times root x. Do y'all agree with that?
Or 4 root.
You're just obtaining a common denominator, aren't you?
No, it would be 4
should
root
get
x.
4 root
times-
x
4 root
over
x
x.
over x.
4 root x over x. I mean, I guess that's one way to look at it. It's not. We'll just put this one here.
Should I put
Yeah, the first 4 should be 4x, right?
Yeah, because it's square.
Oh yeah,
Oh,
I forgot that x. Yeah,
Square root square.
I said it, but I didn't write it down.
But the,
But it's not really that different, right?
yeah,
just change it to the 4x.
4x would make it half.
Yeah.
And then switch it, do the powers and thing.
Right. Yeah, so these are both terms that involve radicals. It would be easiest just to write them as their powers. So we can just apply the power rule. So anytime you see radicals involved in antiderivatives, you automatically want to convert those to their respective powers. So we're going to look at just rewriting this as 4 times x to the 1/2 minus 4 over x to the 1/2, which that second term really isn't great in how we've written it. So instead of saying 4 over x to the 1/2, let's call that 4 times x to the negative 1/2. Is everyone okay with that? Then we're just going to apply the power rule to both of those terms. So what would the antiderivative of 4 times x to the 1/2 be? Okay, 2 over square root of x. The 4 is a constant. It's not getting, we're not taking the antiderivative of the 4. We're just taking the antiderivative of the x to the 1/2. So we're just going to add 1 to the power and divide by the same result. Oops. Same thing with this other one. The minus 4 stays minus 4. We have x to the negative 1/2 plus 1 over negative 1/2 plus 1. Right.
Sweet. I like it.
So we have 4 over x, or sorry, 4 times x to the 3/2 all over 3/2 minus this 4 times x to the 1/2 all over 1/2. And I guess the 4 is really up here, so we'll extend that a bit. Just invert and multiply, clean up your constants. You have 2/3 times 4, so you have 8/3 x to the 3/2 minus 4 divided by 1/2 is 4 times 2, x to the 1/2 plus c. I guess we should have a c out here the whole time. And that's it. I mean, if you want to rewrite it with radicals, feel free to do that. But that's the antiderivative right there. Any questions on that? All right, before we look at the next thing, I want to mention here what we're doing with the antiderivative. The antiderivative is sometimes or more often referred to as the indefinite integral. Indefinite. And so anytime we compute something like that, we're just going to get a function in return. And of course that function is the antiderivative. It's not until chapter 5, sort of midway through chapter 5, where we actually look at what this thing can actually tell us. Like derivative, we interpret it as an instantaneous rate of change. What are we going to interpret or relate an antiderivative to? We don't see that until chapter 5 when we start talking about a definite integral. And when we look at a definite integral, it's almost identical except for we have these bounds up here. So those are just some number, 0 to 5 or whatever, of f of x dx. And this whole thing, once we evaluate that, won't actually come out to be a function, but it'll come out to be a number. There's many different contexts a definite integral can apply to. We're going to primarily just look at one major one of what that number actually will tell us. So you're not responsible for remembering the definite integral stuff, of course, for this test, because we haven't talked about it yet. But it's just, I think it's important to point out, because when we get to chapter 5, it's sort of this slow build-up to what this actually is and our interpretation of it. So anyhow. So if you look on that formula sheet, I know we've done a couple of these, but I think it's important to establish or try to make it clear the connection between the antiderivative formulas you have on that sheet to the derivatives that we already, in theory, should know. So I know we've looked at a few of those. Like, 3, where we know the derivative of the tangent AX is a times secant squared, which implies that the antiderivative of secant squared AX is 1 over tangent times of AX. Right? So the relationship that's coming from is the inverse relationship between a derivative and an antiderivative. And in the chain rule, we have to multiply by the derivative of the inside, which gives us that a secant squared. But then they have that little arrow pointing to the right, saying that if I know this derivative formula, that implies I know the antiderivative formula for secant squared, right? Because if I know what function do I take the derivative of to get secant squared, then I know the antiderivative of secant squared. So again, the way we see that is we're just going to take the antiderivative with respect to x on both sides of the equation. And being that the antiderivative and the derivative are inverses, this just leaves us on the left-hand side tangent of AX. Of course, we've got constants floating around, but so this stuff is undone. This stuff is as it is. It's the antiderivative of a secant squared AX. Yeah.
Why didn't we cancel it out on the second one?
On the right?
Yeah.
Right-hand side, because we don't have a derivative over there. The derivative on the left-hand side cancels out with the antiderivative that we took on both sides. And the only other step here is this a is a constant. So this is a constant times a function of x. So that you can view that constant as like sitting out multiplying the antiderivative. And we just want a formula for the antiderivative of secant squared. So we divide both sides of our equation by a. So the tangent of ax all over a is the antiderivative of secant squared ax. Or 1 over a times tangent of ax. So when you recognize, hey, I know what function I take the derivative of to get secant squared, you're really doing this in your head. I know it's like it might be a little bit tedious with the notation and stuff, but That's exactly what we're doing.
In this instance, can we then root both sides to isolate secant, take that or just secant by itself?
No, so because if we took the square root of both sides, we would have to take it as it is, like that.
So because it's not a constant, we can't pull it out.
Yeah, right. Yeah, if you wanted to isolate secant, then that's a whole different problem. What function do I take the derivative of to get secant? It's not intuitive because we don't have a function that we take the derivative of to do that. So then like other techniques have to be applied to find the antiderivative of just secant. Welcome. Any other questions? So if you'll notice the bottom three, 10, 11, and 12, we looked at the derivative of inverse sine of x, the inverse tangent of x, and so forth. They're starting off with saying what's the derivative of the inverse sine of x over a, or inverse tangent of x over a, just because they give a more common function expressed in the antiderivative itself. So let's look at that one. Let's take the derivative of the inverse tangent of the quantity x over a. So we take the derivative of the inverse tangent of something. It's 1, let me scoot this over a little bit. It's 1 over 1 plus the quantity or the argument squared. Times, by the chain rule, times the derivative of the argument. The derivative of x over a is what? A is just a number. It's not 0.
Might be a over a squared.
No, look at x over a as 1 over a times x. What's the derivative of 1 over a times x? 1 over a, right? What's the derivative of 3 times x? It's 3. What's the derivative of 12 times x? It's 12. The derivative of a constant times x is just the constant. Our constant is 1 over a. So times the derivative of x over a. And so we have this weird expression over here that just gets cleaned up. So we have that derivative of the inverse tangent of x over a. We're just going to distribute the a through the bottom. And then multiply the top and bottom by a over a. Or multiply the expression by a over a, rather. So we have a nicer looking expression for the derivative of the inverse tangent of x over a. So if that's the case, then when we take the antiderivative of both sides, we just get the inverse tangent of x over a over here, and the antiderivative of a over a squared plus x squared. I mean, I think ultimately you'll just end up remembering the formulas versus going through this process. At least that's the hope. It's not entirely efficient to to do this, although you could get all of those antiderivatives because you know all of the derivatives. It's just not an efficient process. So we could leave that as an expression for the antiderivative, or sorry, for the inverse tangent of x over a. But again, what they do is this a up here is a constant that's just multiplied by all of that stuff. So then we'll divide both sides by a. Oops. And then that's your expression or formula on that sheet for the antiderivative of 1 over a squared plus x squared. So when we have those like linear type arguments, you'll notice all of the ones on our formula sheet the antiderivatives do involve that 1 over a. The only exception there is number 8 with the exponential, because we're not dealing with multiplying by a. But specifically number 10, like the inverse sine and the inverse cosine don't involve the 1 over a thing for their antiderivatives. All right, so that's, I think, an important connection between those operations, derivative, antiderivative, and when you look at that formula sheet, hopefully it's a little bit more clear as to why all of that stuff is there. Does anyone have any questions on this? Okay, so here's 4 antiderivatives. Why don't y'all take 10 minutes to compute those?
Okay, root first of all, second of all. You drop me after you go to your next colleague, I'm watching you. So you're aware. I'll come back and comes out of nowhere. Just starts and goes outside your house. Just stands there. You're dying, like not even parking. He's just looking at me. Brian's like, he was like him. Just close the blind. But like I'm facing the opposite way. I'm facing the street. You haven't even invited me over, which is so fine. I'm not hurt by it. You want to come to game night? What's game night? On Saturday. Probably Saturday night because you hate game night. We can have another game night. Yeah. We should also study. Yeah. Just like in general. Well, we also said we were going to go on that double date and we never did. Yeah, there's a lot of things we want to do. Like this one.
Oh, I was looking at, I was looking at this, I'm like, what are you doing?
We're not doing that.
Okay, that, got it, that's.
Yeah, that's the 22nd part. So that matters.
So it would be 1/2 times. 1/2 is 1
Would it be negative?
Oh, yeah, see, there's a negative out there. You get that sign down there. 1 over, negative 1 over.
Plus
Plus the inverse cosine, which is 1/2.
Wait, would it be 2?
1 over a.
Would it be 2x because of the AX?
Yeah.
So it'd be
So it's a
negative
1 over
1/2
a
cosine 2x.
cosine, yeah. Or you can just simplify it, call it negative cosine 2x.
And then use cosine.
Yeah, that's great.
Cosine.
I like that the quadratic is not too big, so we
Is that all you have to do? Or do you have to
yeah.
Nice.
That's what I like. 5 days. Because I was like, we had it on Thursdays for like the last 2 camps, and I'm like, frantic to get all the homework done, everything like that, just to finish it up. Like, well, even though I just did the quiz this morning.
The best.
But it's nice.
He's like, are you gonna pass?
So I'm like, I don't study.
Are you gonna pass? Give me a couple of
Because you're
Oh, yeah.
People are like, hurry, do some work. Never tonight, you're like, yeah, for sure. Takes the entire bottle of wine. I'm ready. And then you're like, really forgot. Like that.
Like, yes. That's how we're trying to figure it out. Well, it's only like till week 4 week, and then we're done. Then it's whatever.
well, you do when you're choosing the derivative. Because you have to take the derivative.
You can take up the start to like
Look at your campus.
Yeah.
Somewhere in there.
Yeah, it's over a month.
What do we do with the 5?
It's a constant without and you just like set it over for Thanksgiving.
Okay, cool.
Take the interval. Because if you set the derivative of 5 times
Because the,
whatever the derivative of tangent
For like a few months.
yeah. It's just a constant, but I just didn't know what to do with it.
Yes,
Stays in
you
there.
just sit out here one
Yeah, I was like, how long?
And then do I put it back in?
Yeah, then you gotta get the
Like
5
bears,
half.
sleep all winter, and then wake up in the spring. It's like, all right. Because then we would have like a food problem.
Yeah, I left it one just to make myself.
Because I mean, like, even like the female bears, they have their babies while they're born. And they wake up and they're like, I have kids now, you know? And it's like, it's weird. Because they give birth and everything while they're
Yeah.
What did you guys get for that?
5 tangent x plus
Plus C.
I mean, the answers are kind of based on the Yeah, like, really self-working.
Call this. Could you call this 1 minus x times x to the negative 1? Oh, and then it's a product. Oh, wait. Just split them up. You can just split them up. You make 1 over x. Yeah, that's the line. That's natural. Split it up.
So, with this
Let's try this.
This technically is the easiest. Yeah, right.
Hey, what do you do? So I just multiplied it by x over x.
And then bottom would be x squared. Yeah, just split it up and then it's ln x minus x minus
Not cube, squared, No, wait, no, that's 2x, never mind. Difference was 2x.
So for number 3,
when you take the derivative, except there'd be a minus x there because it's still a minus.
No, you did. So, oh yeah, you have to do the chain rule.
so for number 3, is it product rule and then you solve it?
Product rule here.
Yeah, because you can't like do the
Yeah.
because we haven't learned.
Basically, this is all.
Correct? Am I right?
You're correct, yes. But when you take the integral,
Because I looked at the
when you take the
cheat sheet of
derivative
like,
of,
and I like again.
Oh, I see why that happens. Okay, that makes sense. Because
you take the derivative, you get
chain rule that makes it.
which we have secant tangent.
So that would be secant 3x.
Yes.
Well,
So you do 1 over a secant
What? Oh, it should be 1/3.
Yes. Because when you're taking the derivative of the equation, you have to take the chain rule. So you take the derivative of 3x, which will equal 3, and so to negate that, you do 1 over.
so you'd have cosine 3x. Or you'd have
Fourth one
3
is
Why don't you
1 over x.
3 then? Why don't you do it? So you're saying for 2
Oh wait,
One minus x. Yeah.
1 minus x over x. That's it?
I'm just thinking about it backwards.
It's weird that you don't make this too.
I like these ones better.
So with this one, you can do my integral. Split this up to 1 over x.
And this would turn into ln.
yes.
I really love
That
how
extra
much
break
more
one
sense.
got 1 over x minus
So if you
ln.
let's just do cosine. Say it's the integral of
no,
cosine.
minus x. When you take the derivative of,
Oh,
when you integrate 1,
Okay, I don't know why I got.
antiderivative. And this
So
has to be
if you have the
absolute.
derivative
oh, you're right. I forgot about that.
Because the function of ln of x is like this, and then
what is the number? I was thinking about the
Right, that's right.
And then isn't there
I think it's just like.
there's on the second page. There's 1 5 times.
So like, this is how I would look at it. And then I would say, oh, well, I know what this is. That's tangent.
that looks like
And then you have 5 times all of that. So it's really 5 tangent.
Because that's
X
true.
plus 5 times.
Okay, so we can just say.
So we can just call that.
Oh, yeah, it's true. Is it,
figured it out. Yeah, it's inverse sine.
It turns out.
That's what I was.
Yeah, when there's a 1 up there, you can move the dx up. Or the 1, that's down. Like, it's down the dx up. There's a 1 there. But it's one over root a squared minus b squared, which is the same. If you just write the different sign, yeah, if you take the integral of that,
She's like a
sign
holistic
x over here.
chiropractor. You're like, all right, let's get going. It's almost the weekend. You're almost there.
There's also a healthy part.
My professor was like, yeah, so we have an essay due next week, but I was registered for that one. Everything's great. And he's like, everyone needs like really close attention, so we're just gonna push that off. Like, and I'm like, it's literally the same paper in the history of yeah. Yeah, and like English is English too.
Plus x, it would be x over here.
According to this, I don't know why.
It's like, all right, that's your introduction. Okay, cool. We got one page. I have this new guy.
That's what I thought.
So this should be a 1.
I feel like,
Okay, that makes perfect sense. Then it's 1 over 12 and 1 over...
but it's just like I'm so lucky class. This is like 4 years ago. No, it was like 6. It was like 5 or 6 years ago. She still works here. Yeah, she's like the dean or something. She's like in charge of the English department or something.
I think that's
She probably goes.
We have no idea why.
I'm a simple creature. I learn one rule and I follow it.
Yeah, exactly. So if I take the derivative of sine of 2x,
2 plus 2 equals 4.
then I say that's cosine.
Times the derivative of 2x.
So, but that's for the derivative. I'm multiplying by that 2. If I take the antiderivative, I want to divide by that 2.
Oh, I see.
I mean, I know that's not technically correct, but
Whatever.
that's what
No, I what you're getting at now is it will apply to the derivative back to divide, right?
That's where that division by 2 and
Why didn't you say that?
I'm sorry. Really, I'm sure I'll watch that.
I think it's Donna Gray. Just kidding. There we go. Yeah, it's basically like expanding your writing, and it's like, I'm not like, I don't like writing, so I just like, I turned in something. Yeah.
it's commonly forgotten.
I mean, yeah, I tried.
It's like 16 minutes long.
Oh no, I'm thinking there.
She first defines the term equals and what equals.
Yeah, I'm agreeing.
She literally
She's a department chair.
Oh,
Also. No, let's give her my postseason class. I just saw her name and I was like, I can't hear her. And she's not the department chair, so that's how it
Oh my god, do like the basic white, like big sweater.
Like a lot of people
High heel
took
boots.
my first math classes because I took the zero class.
I'm fine wearing high heels if I can sit most of the time.
And I took it with
Oh, yeah. But if you want to
my and she's like, I think one of the directors. And I've seen her like sit in the classes. So I'm taking some like math classes here, and I've seen her like, she's the one who like grades the professors and stuff. Yeah, they do. So she's got like all the time.
Yeah.
should just like
Forward your makeup, you just
we can find out.
And I was like,
I'll just get to the end where it has the entire full.
okay, so there's,
I'm
so
trying to show you
calculus is our class, and the class I took for this was pre-calculus, which was trig
I really kind of thought it was like
Basically, just like S1 equals 2, S2 3, so I forget what it's like the next number, if that makes sense. So it's like I don't know what was so intriguing about it, so like this one triple example, so okay, now I know
instead of getting the big extravagant thing.
I never given an entire
So there's, because I can't wear that.
I like
Oh, I know, it's like, I've seen some more. Does that make it easier, though, to like understand it?
I wanna know what's different. But this, someone was complaining about this machine.
Yeah.
I was like, that's not.
Hey, just wanted to point out this chart that you're looking at. If you're just going to use this chart, which I think at some point you should know this, you're let me see this. You're ignoring all of this stuff. The only thing you're focusing on are the formulas that actually involve an antiderivative. Right? That's really all you want from that formula sheet, because those are the antiderivatives. Again, the thing on the left is just saying that if you know a derivative formula, then you know some other antiderivative. But if you're going off of this chart, make sure that you're just focusing on the antiderivatives. Does that make sense? You already know the left-hand side of that chart. Okay. Well, I got super quiet. I know some of you are still working through, but I just want to at least write these first two down, and we can scoot it down. If you don't have the notes, you can see the next two. But the antiderivative of sine is negative cosine, because the derivative of negative cosine is positive sine. So that's different, right? We take the derivative of sine, you get cosine, but the antiderivative of sine is negative cosine. if we took the derivative, we would multiply by 2, right, by the chain rule, but we're taking the antiderivative, so that's why we have to divide by 2. So the antiderivative of sine 2x is negative cosine of 2x over 2. The antiderivative of cosine is sine. Antiderivative means we're going to divide by 3, not multiply by 3. So this is, if you're referring to that chart or the sheet, this is number 1 with your a equal to 3, and this is number 2 with a equal to 2. Oops. Just kidding. Is everybody all right with that? I don't know what's best for you at this point, but if you are going off of that sheet, then that's what you're looking at. Plus c. And then 5 secant squared is just 5 times the antiderivative of secant squared. And so that's just 5 times tangent. And so the thing with that is if you pull the 5 out, you're going to have 5 times the antiderivative. The antiderivative is going to give you tangent plus c, but it's 5 times tangent, 5 plus c. 5 plus c is just another constant. So we could I would just recommend not trying to keep up with all of the constants. If you split it up into 10 different antiderivatives, you just find the antiderivatives and at the very end put a plus c. It's a little bit different when we look at other problems, but when we look at other problems, it's clear that you need to keep track of the constant. For just strictly finding antiderivatives, just put the c in at the end. Okay. Did anyone have any questions on either of those two?
Can you go back up to the top one real quick?
Mm-hmm.
Okay, cool.
All right, so these other two. Do y'all need a few more minutes to do these? Yeah. All right, so we'll take a few more minutes.
And I want to go buy the bathroom. And then I was like, I'm on my wallet.
I did. I was doing my car. Oh, it's not a... basically, I don't have a heater. My family insisted I get it fixed. And now it's going to be wildly expensive to get it fixed.
That's why I read the description. The description gave me anything goes wrong. I'm like, it's just a
Bye.
they are. I got a donation for it. They tell me how to do it. There's some reason I'm doing it by hand.
It's not that expensive.
3x is 3, right? Since you're dividing by 3, it gives you
Yeah, I
that.
drive 20.
From what I remember, taking the antiderivative not essentially
Yeah, that's all.
we're two.
It's so weird.
Yeah, so what was the explanation?
Why that's three.
Because it's, that's what it's defined.
I love my car.
It says like.
Like, I'm smarter than you want.
It's just a specific. It says the antiderivative of this function is some function capital.
My car's name is Midas.
My boy turns into like really long and I'm like, I'll just cut your hair. And he's like, no, I'll cut your hair. Like, what are you doing? Cut your hair.
Oh, Brian,
Yeah.
Get a GOI.
You're allowed to have
Just the function.
My dream car is a matte black.
Like more in like a more technical way to the derivative.
But like literally.
Basically, whatever equation you have inside of the sine, send out
Maybe they were saying because we looked at it, we looked at it like now. Because you can have that as like efficient. You don't actually just get that because the antiderivative over all of that.
I feel like it just looks weird. Like,
It does. The fact is if I take the
like when you have the X
then I just get they're all by constants, right? The way the antiderivative is.
and then it like goes to the weird looking function.
I don't know.
$20.
I don't
Drop the battery pack, slot another one in.
I don't like usually.
Batteries are universal switch.
That's
I
like
just
kind of
really
like
are.
better
I love it. Look at how sick that is.
oh wow, it's been an hour already?
My little bread.
We got 15 minutes.
Oh, wait.
3 minutes of break. Usually like 2.
Can that should be my box.
Around 2.
So the final one, you would want to simplify that first. It's a quotient, so simplify it first. And just, again, another technical thing, but the antiderivative of 1 over x is the natural log of the absolute value of x. Minus x plus c for that last one. All right, does anyone have any questions on those 4?
The only reason that natural log is the absolute values because the x values will always be positive, right? Because that's the the function of the natural log.
Right. Right, and the other reason is when we start connecting, interpretations to the antiderivative, it matches up with the domain more closely.
Yeah.
Right, because if I do 1 over x, it's not defined for only 0, but the natural log is only defined on the positive part over here. So they're defined. The natural log is defined for like half of the function 1 over x basically.
But if we do the absolute value of that, we get more agreeance upon their domains. Oh, it doesn't like that. Let's start over. Why isn't it crafting that? Something weird with the, oh, maybe I need to do this. Here we go. So there's the absolute value, or sorry, the natural log of the absolute value defined for every number but 0, just like 1 over x is now. And also, we really didn't go into detail about the derivative of the natural log. It's there on that formula sheet, but the derivative of the absolute value in the argument for the natural log, that's still just 1 over x. Okay. Any other questions on this? Okay, so there's sometimes, specifically with the example 1 and 2 below, it doesn't apply directly to your formula, so you have to manipulate those a little bit. This one here, we'll take a break after this one. The 1 over root 144 minus x squared, what would that be? Which one? Yeah, so if we think about it that way, then what does that lead us to? Should have left a little more.
Inverse sine.
That's for the inverse sine, yeah. So now this one here is of the form number 10 with a equal to 12. So it's inverse sine of x over a. So, I mean, when you see something like that, it is a little bit different, right? Because we never actually took the derivative of 1 over the square root. Well, maybe we did, but when we're thinking about the derivative of 1 over the square root of 144 minus x squared, now we have to kind of think in reverse. Okay, well, what function did I take the derivative of to get the form of 1 over root something squared minus something else squared? And that came from inverse sine. So it is a little bit of a shift in thinking to get these, which is why I think it's easier to first, just look at where it comes from, but then just remember what's on that formula sheet. And even when we talk about techniques to evaluate that without using the formula sheet, the technique that we use is, I think, lengthier than just knowing that's the inverse sine. So even when you have techniques, it's not as efficient as just knowing those basic antiderivatives. Do y'all have any questions at this point? All right, so we'll take a break now.
All of your classes. Yeah, no, I just get so scared that I can't.
All right, so with this example here in mind, what would we need to do here for the 1 over 16 plus x squared?
Would you do 4 squared so that it can be the inverse tangent?
Right. Yeah, we want to look at 16 squared. It's the antiderivative of 1 over 4 squared plus x squared. And so there, your a is 4, and the antiderivative is inverse tangent. So it's 1 over a times the inverse tangent of x over a. So specifically with this, the inverse sine and the inverse tangent, that a squared is not going to be, usually it's not written out as a square. So you have to sort of rethink of it as or some quantity being squared. Does anyone have any questions about that? All right, you kind of have a similar thing here with example 2, but we have a 16x squared, and the one on the formula sheet is just in terms of 1x squared. It's not a squared plus, you know, b times x quantity squared. There is no number in front of the x. So the way we want to think about this was pull the 2 is a constant multiple. So we'll just put that out front and deal with it later. 1 over 16x squared plus 25. And then so to fit that to the formula sheet, what do we need to do with that?
Do the quantity 4x squared plus 5 squared.
Yeah, so if we did this, does our formula apply to that? I mean, yeah, it does, but you've got to be careful on how you put things together, because it says that this is 1 over a times the inverse tangent of x over a, right? And we could think about this x right here as just being something squared, right? But that something is also here. So if you're gonna approach it from that route, you need to be a little bit more careful. Since we're going off of that formula sheet for the time being, and it does have just a 1x squared in that formula, something like this, we wouldn't want the 16 next to the x squared, so we would have to factor that out. But I can't just factor the 16 out of the x squared, right? I would have to factor out the 16 from the entire denominator. So in order to have that as a 1x squared, I've got to factor that 16 out of both of these things. Does that make sense? That's the only way you can get that to be, if you're trying to get that to be a 1x squared, that's the only way you could do that. And then we can view that, again, this is 1/16 times this function. The 1/16 is just a constant, so we can take that out and deal with it later. (25 over 16 is 5 over 4 squared. And then we can look at this from the table with a being 5/4. So our constant, we've got a 1/8. The antiderivative is 1 over a. So 1 over 5 over 4, 1 over a, times the inverse tangent of x over a plus c. Which step? Here?
For the final answer, how did the 216 become 1?
So the 2/16 we just reduced as 1/8.
Oh, yeah, okay.
And then the rest of it was from the antiderivative, yeah. And then so we'll have our 4/5 times 1/8. That's 1/2 times 5, 1/10. Inverse tangent of 4x over 5. Say plus a constant. We'll just call this a different one for now because it's multiplied by the 8th. But it's 1/10 inverse tangent of 4x over 5. So that's one way to look at it. Then once we've seen this as it emerges from the formula, we can go back to the other representation we had, just to kind of see where those things have to go. Do y'all have any questions on this process? So some of them aren't like as straightforward as just applying the antiderivative to the formula sheet. Some of them, like this last example, do involve a little bit of work. All right. So the other thing we can do with antiderivatives at the moment is talk about differential equations. What does the word differential mean? What do you think about when you hear that word? Derivative, yeah. So differential equations are equations that involve derivatives. And the point of a differential equation is to find the original function. So you might have like a differential equation that's like the second derivative of a function plus the first derivative of a function is equal to 2. Let's say, for example. And what we want to do is find the function that satisfies that equation. Ours are a little bit more straightforward. Differential equations is just an entire field of math all on its own, just because there's so many different ways to solve them. They are very complicated, but we do look at a really specific type of one here that we call initial value problems. And so initial value problems are just, for us anyways, they're problems that involve the derivative and some initial value on the function that we're after. So this right here, this f of 0 equals 1, that's our initial value. And so we're given a derivative is 10 e to the negative x and some initial condition on the function itself. With that, we're able to find the function that satisfies one derivative is 10 e to the negative x, and if we plug 0 into that particular function, we'll get 100 out of it. So how would we figure out what f of x is if we're given f prime?
Antiderivative?
Right, yeah, if someone gives me the derivative, as they've done here,
to get back to the original function, I just find the antiderivative. So we're going to say, like a general statement is, if I take the antiderivative of a derivative, I'm going to get f of x plus a constant. Does everybody agree with that? Being inverse operations, antiderivative here. And then for this constant here, we use the initial value or initial condition to find C. So what we have is the antiderivative of 10e to the negative x with respect to x. And what would the antiderivative of 10e to the negative x be? Yeah, negative 10 times e to the negative x. Does everybody agree with that? So this is like the one on your formula sheet, but a is equal to negative 1. A times e to the ax, negative 1 times e to the negative 1x. Plus c, right? I take an antiderivative, we get this generic constant. So that's the antiderivative of our derivative. We see that we have f of x plus c. I'm going to erase that. So then we also have a condition on that function. And we know if we evaluate that function at 0, we should get 100. So it's a different f of x, but we'll call this, the whole thing we'll call f of x. Just from the antiderivative. And then at this step we use f of 0 equals 100 to find c. So we know f of 0 is equal to 100. But we also know f of 0 is the same thing as negative 10 times e to the negative 0 plus c. I'm going to write this out here too. And so we just have an equation involving the unknown c. One equation, one unknown allows us to solve for c. So we have 100 equals to negative 10. E to the 0 is 1. So we have 100 is negative 10 plus c, which means c is 110. And then so we just fill that c in. We have f of x is negative 10 times e to the negative x plus 110. And so that function there is the function who satisfies the initial condition and the initial value and the fact that the derivative is 10 e to the negative x. Do y'all have any questions on that? And so really the main thing we use that for is when we look at those motion problems with position, velocity, and acceleration. Those are initial value problems. So from chapter 3, we were given a position function,
And then we said if I take the derivative of the position, I get the velocity, and if I take the derivative of velocity, I get acceleration. But in chapter 4, we're given a of t and we find the velocity and the position. So antiderivatives, we're reversing the process. Starting off with acceleration, how do we find velocity? If I know the acceleration function, what is the velocity function equal to?
The antiderivative of the acceleration.
The antiderivative of the acceleration with respect to t. Do y'all agree? We're missing one fine detail with this though. If I take the antiderivative of acceleration, I should get v of t plus c. And so that's an initial value problem. We have the derivative, we have f prime, if you will, as a of t, and we're finding the function f of x, or v of t here. Depending on the velocity function, well, I guess always, use initial value or velocity to find c. And then once I find the velocity function, how would I get the position function? Take the antiderivative. So the antiderivative of our velocity function is equal to the position function. Well, I mean, just being really technical here, we'll condense this to, in a moment. So that c would then be anti-differentiated too. That constant antiderivative with respect to x would give us c times t. And then when we get some other constant here, we'll call it c2. Doesn't really matter. But again, that constant coming out of the antiderivative of the velocity, we use initial position to find c, too. And that's the more technical way to think about it. The more condensed version is that the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. It's not really a technical way to write it, but to think about it that way isn't entirely wrong. So specific example, if an object is thrown upward at time equals to 0 with a velocity of 40 meters per second from the edge of the cliff, that's 100 meters above the river. A of t is negative 9.8 meters per second squared. Find the velocity for all times larger than or equal to 0. So our velocity function will be the antiderivative of the acceleration. What's the antiderivative of negative 9.8 with respect to t? Yeah.
Let's see.
Negative 9.8 t plus c. What's our initial condition on velocity?
40 meters per second.
It's 40 meters per second. It says an object is thrown at time equals 0 with a velocity of 40. So our initial value for velocity is that velocity evaluated at time 0 has to be 40 meters per second. C is 40. See, like when you're dealing with polynomials, the initial value is always the constant because everything else zeroes out. As long as you're starting at a 0, like time equals 0 or x equals 0, right? But in using that, we would say, all right, well, the initial value v of 0 is 40, so v of 0 is 40. But we also know that v of 0 is negative 9.8 times 0 plus c. So we have 0 plus c is equal to 40, or c is equal to 40. So then we just want to put that back in here for c and say that velocity is negative 9.8 t plus 40. If you don't remember that constant, when you find the position, your position function is going to be way off. So we've got a velocity function, then we can find the position function. The position function s of t is the antiderivative of velocity. So the antiderivative of negative 9.8 t with respect to t would give us what?
Would be negative 9.8 t squared.
Yeah, negative 9.8 t squared over 2 plus, add 1 to the exponent and divide by the result. Antiderivative of 40 with respect to t would be 40t plus.
So that's the c subscript 2 that you were talking about?
Yeah, so that'll be a different constant in general. Sometimes they might be the same, but we'll just divide here. So we have negative 4.9 t squared plus 40t plus c as the position function. What's the initial condition or value for position? 100, yeah, because it says at time equals 0, the object was thrown like this at 100 meters above. So the initial position, s of 0, is 100 meters. Again, we'll use that to solve for the c that comes up with our position function. Okay, so S of 0 has to be 100. So C is 100. So then S of t is negative 4.9 t squared plus 40t plus 100. And so for like these quadratic position functions, we could have just used like really arbitrary things instead of 40 and 100. In general, when you look at a position function that's quadratic, you'll have negative 4.9 t squared plus the initial velocity times t plus the initial position. So that's how they're structured. This would be different if it was, if we're talking about feet per second. This is valid for meters and seconds for our units. But that's the basic idea. Do y'all have any questions on that? There's going to be one like this problem on your test. So. With these problems, you should still be familiar with things like finding the maximum height. And other stuff like with what velocity does the object hit the ground, stuff like that. Etc. But those problems involve you finding the position function, the velocity function, and then answering questions about that scenario. Does anyone have any questions? Okay, well that's 4.9 then.
Done.
So as far as the content of the exam, there's going to be 10 fill in the blank or true false questions. One question where you're given a function, given f of x, state the intervals, where f of x is increasing and decreasing. And any local mins or maxes. So that's where you come up with the, depending on the domain of the function, you come up with the interval or the test line for your derivative. You plot your critical points, and then you test on either side. There's one question where you have to do the same thing with concavity and inflection points. So given f of x, state the intervals. Where the function is concave up and concave down. And also inflection points, any inflection points if applicable. Similar situation, but you would use the second derivative for that one. Whatever that happens to come out as.
Hey, Cody,
Yeah.
Is that the one you said you'd give us both f prime and f?
No, I didn't actually decide to do that on the graphing ones
Okay.
because I didn't give a rational function.
Okay.
Yeah. So on the graphing ones from 4.4, it's just going to be something that the first and second derivative isn't difficult to find, like or as complicated as a rational function would be. Or some of those ones in your homework. The one the other day was like 5x times the natural log of 3x or something like that. It wouldn't be anything that convoluted. So then that's from 4.4 given a function graph using methods from chapter 4, and I'll have like a checklist below that. So I'll say make sure you identify the domain, the intervals of increasing, decreasing, etc. So you're coming up with this kind of picture for your function. Decreasing, concave up, increasing, concave up, decreasing. You know, that stuff from 4.4. One question one question where you're given a function on a closed interval from A to B. You want to be able to find the absolute maximum and minimum. There's going to be 4 limits. They all could be L'Hopital's rule. So you should definitely know those cases where we had these two that directly apply to L'Hopital's. The indeterminate product for sure, and the 1 to the infinity, 0 to the 0, and infinity to the 0. There's 5 antiderivatives. We sort of continue with antiderivatives in chapter 5, so that's kind of where we end in Calc 1 with antiderivative stuff, and then where Calc 2 begins. So we'll see antiderivatives again in chapter 5. I have antiderivative questions. One question involving motion. You know, where we're given an acceleration function.
Is that part of the 5 antiderivative questions?
No, it's different. I mean, it is antiderivative, but it's a different kind of question. That's it. We had to cut some material, so that's what we're dealing with. So if there's anything specific from there that you want to address, we can do that, or if you have other questions. Yeah, go on.
So for the motion given at AFT,
Yeah.
is it the same as the problem we just did?
Yeah, right,
Yeah.
right, exactly. So there's specific things y'all want to talk about or look at?
I just have one quick question.
Sure.
For the graph using methods from chapter 4, is end behavior one of those checklist items?
Could be, yeah. Could be, you know, not only just stuff that appears in chapter 4, but anything from chapter 3 with limits and stuff for vertical asymptotes, horizontal asymptotes is still fair game. Any of the previous stuff is still on the table. So, homework questions about any of these topics?
It's number 13 from 4.3.
4.3? Okay.
F of x equals negative square root 5x times ln x 4x.
ln of 4x?
Yeah. And you have to find the concave balance.
Oh yeah, this one was, someone else had a question about this. It's really quite tedious because the derivatives, the first derivative is not too bad, but the second derivative is, there's 2 quotient rules. Yeah, so, is it negative here?
Yeah, the negative is outside of this.
Okay. So, all right, intervals of concavity. Intervals of concavity. So we have first derivative, we need the second derivative for intervals of concavity. We have the first times the derivative of the second. That's 4 over 4x plus the second times the derivative of the first. The negative 1/2 5x to the negative 1/2 times 5. For the derivative of negative root 5x. Now, I guess it's a matter of preference at this point in how we write these things, but we do have to take the derivative of this function, so I don't know how you want to write it, negative 5/2. Leave it like that. Maybe we want to write it as the square root of 5x, or sorry, 1 over the square root of 5x. We want to leave this as the quantity 5x to the half. I don't know that it matters too much at this point. So we've got to take the derivative here as it is, quotient. The derivative here, again, is a product rule. We could look at it as a quotient if we put the 5x to the negative 1/2 in the bottom. So I suppose it's just a matter at this point of how you want to look at it, quotient rules or chain rules. Do y'all have a preference?
I tried doing it as a quotient rule, and that's where
Yeah, it gets pretty messy.
fell apart.
I had honestly thought I'd deleted this problem from your homework just because it's such a pain.
No, you still got time.
Huh? Yeah.
So you got time.
Still have time.
Until Tuesday.
It's like you can see the answer should be.
Okay, so if we're going to look at that as a quotient, I'm going to rewrite it once more. Yeah, the 5/2 is a constant here for this one when we take the second derivative. -1 we'll leave out, so we'll have this -1 bottom times the derivative of the top. Minus the top, just put this in parentheses, minus the top times the derivative of the bottom. Oh, okay, we'll just leave it like that. All over the bottom squared. Shrink this a little bit. So that was the first term, then we've got to take the derivative of the second term as well. We'll just pull that 5/2 out. Again, another quotient rule, bottom times the derivative of the top. That's 1 over x again. We'll just write this over x. Bottom derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. So it doesn't, it's not very nice, but that's what we have. Distribute the -1. Here, so we'll have negative, yeah. I guess we'll just write it out and then see which way is the best to tackle simplification. -x over 2 over the square root of 5x times 5. We'll have that one as a first term, and then we'll have plus well, I guess it's all over x squared, so here we have our x squared here, and then plus our square root of 5x there. Over x squared, sorry. So both of those are over x squared. What do we have here? I guess we can put our -5/2 back in. We have 5 times root 5x over 2x over 5x plus 5, what do we have here? 5 ln of x times 1/2 over root 5x times 5. Right. Now we already have the times 5. There's a lot going on here.
Yeah.
Just making sure we're keeping up with everything correctly. 5's over here, the ln, and we're multiplying that by 5/2.
So I just take the problem off.
Yeah, I don't know.
Just think about it.
I'll think about it, but it's nice to struggle sometimes. No struggle, no growth, right?
Bill's carrot here like mosquito bites.
Okay, so does that look all right?
Even a little bit.
The only thing I'm wondering.
Oh, that one's over 5x too. I mean, it's like that's the idea now. We've got all these fractions that we can invert and multiply, simplify, clear the fraction. That's the whole process that we're going through. Not sure that we did that. Let's just double check our distribution. Over 5x, and then we have 25/4 ln. Yeah, all right. I think that's okay. So we have -5x over this plus this this 5x will come in the bottom here, so we have 5x is there, not here. Not here anymore. So we can just divide these. Oops, I don't know why I wrote equals. So what do we have left? Plus root 5x over 2x squared. Same thing here. That 5x comes into the bottom. So that's 5, that one. derivative. Hey, what? Okay. So then, in order to find the intervals of concavity, we have to determine when our second derivative is undefined and when our second derivative is equal to 0. So undefined when x is equal to 0, I think that's pretty clear.
Yes.
X can't be 0. And then, I don't know, maybe the best thing to do here is just to get a common denominator, because we're trying to figure out where the second derivative is equal to 0. We just need to figure out where the numerator is 0. So what's our common denominator? 2x squared.
8x squared, 5x.
Root 5x. Remember, if it's kind of overwhelming, just multiply all the denominators together. So we have this 2x squared, need a 2x, need a 2 there. That's fine. We also have this 8, right? So it needs to be that. So what we need here is a 4. What we need here is a
Root 5x.
8 root 5x. Or we need a 4 down here too. We need a 4 root 5x here. 4 root 5x here. And then an x here and then an x here. Minus 20x, we have a 5x times 8. 5x again times 4. And then we have a 5x ln 4x. All over the common denominator. So second derivative is 0. Second derivative is 0 when our top is equal to 0, when 40x plus 5x ln 4x is 0. So take out greatest common factor of 5x. Factors equaling 0 when 5x is 0, and when 8 plus ln 4x is 0. So when does the natural log of 4x equal negative 8?
Never.
Never?
Oh, wait, no.
Natural logs can be evaluated at negative numbers, but natural logs output all negative numbers. So if I say e to the negative 8 is equal to 4x, so I initially come up with these. I had the second derivative couldn't be 0 at 0. But before we label any of those as as zeros or undefined for the second derivative, we have to go back up to the first derivative, or the function rather, and say when does that, or what's the domain of our function here?
0 to infinity.
Yeah. So the interval of interest doesn't include 0 anyways. Second derivative is undefined at 0. We're not going to put that on the line for the second derivative. Yeah, so that doesn't contribute to a 0 or undefined. This is not a part of it either. you just come up with one value that you have to test on the second derivative. So we just have two places to test. So maybe we can test e to the negative 9 and e. Into the second derivative, that giant huge mess.
What was the question asking for, when it's concave up or?
Yeah, concave up, concave down, is that right? So there's, well, I mean, our second derivative is really just 40x plus 5x ln 4x all over 8x squared root 5x. So notice the denominator is always positive, right? So let's just plug in our critical, or not our critical, but our 0 into the numerator of the second derivative. 45 ln 4. Denominator is always positive. E to the negative 8 over 4. We've got 40x. Oops. E to the negative 8 over 4. Oh, well, we're not testing that in there, I'm sorry. We're testing the two red ones. Has anybody computed those yet?
I'm almost there.
Okay, thank you.
It's positive. Is that all you need?
Yeah.
For E?
For negative 9,
Positive?
and E can just be e to the 1, right?
That's gonna be, yeah, that's gonna be positive, because the numerator is positive,
Yeah.
right? Looks like it looks like it's concave up on its domain.
Just like that.
It's not, I don't know, I went through that pretty quickly. I'm not confident I missed a sign somewhere, but it didn't turn out to be terrible, right?
So
Yeah, so like, if you did that,
Like a that was just puts concave up. No.
Did that, this one is actually defined.
Go to that study session.
That way. We're about walking that way anyways. But just stay, I don't want to throw that over. Because if you go, yeah, if you stay on this floor, it'll take you.
And that means I have to walk back by myself.
Like just follow it all the way down. It's just kind of zigzag.
Right, it's kind of a short.
It just looks like sparkle.
Honestly, this one would be so much more fun if it like did sound like a rainbow.
You're gonna see me.
There's